Dear students, this is Dr. K. Saravan, Associate Professor, Department of Information Technology, R&D Engineering College. My dear students, now we are going to discuss loosely coupled configuration in 8086 in detail. This loosely coupled configuration microprocessor system has a multiprocessor where the individual processor configured with their own memory and capable of executing users and operating system instructions independent of each other. This type of architecture paves the way for parallel processing. The loosely coupled multiprocessor systems are connected via high-speed communications network. The loosely coupled multiprocessor systems are also known as distributed memory as the processor do not share physical memory and have their own I/O channels. And this loosely coupled configurations a shared system bus, data bus memory and system I/O. Each processor has its own clock as well as its own memory in addition to access to the system resource used for medium to large multiprocessor systems. Each module is capable of being the bus master. Any module is capable of being the bus master. Any module could be the processor capable of being a bus master, a coprocessor configuration, or a closely coupled configuration. This is the diagram of this multiprocessor loosely coupled configuration. A multiprocessor system makes use of more than one CPU along with memory and I/O channels. They are capable of processing multiple instructions, multiple data, which is called as MIMB programming. Thus, they support a concurrent programming and operations too. The configuration of processor in a multiprocessor systems can be loosely coupled or tightly coupled. The major distinction between these two types of multiprocessor is the way a memory is organized. A tightly coupled system shares a single memory space and share information through a shared common memory. But this loosely coupled multiprocessor consists of distributed memory, where each processor has its own memory and I/O channels. The processor communicates with each other via message passing or interconnection switching. Each processor may also run a different operating system and have its own bus control logic. These loosely coupled systems are less costly than tightly coupled systems because they are physically bigger and have low performance compared to tightly coupled system. The individual nodes in the loosely coupled system can be easily replaced and are usually inexpensive. The loosely coupled systems also draw more power than tightly coupled systems. The loosely coupled systems are more robust and can resist failures. A single node failure does not break down the entire system, and it is also easy to add node more to an existing system. But the need for extra hardware required provides communications between the individual processor, make them complex and less portable. Some of the characteristics of loosely coupled multiprocessors are distributed memory, low contention, high scalability, high delay, low data rate, low cost, static interconnections, capable of running multiple OS, low throughput, low security, increased space requirements, high power consumption, reusable and flexible components. No direct connections between these modules. Each share the system bus and communicate through the shared process here. The processor in the separate module can simultaneously access their private subsystems through their local buses and perform their local data reference and instruction fetches independently. This results in improved degree of concurrent processing too. Excellent for real-time applications as separate modules can be assigned a specialized task. There are three bus allocation schemes available. One is basic chaining and pooling and independent. Coming to the basic chaining, need a bus controller to monitor bus busy and does record signals. Send the bus grant to a master. Each master either keeps the service or pass it on. Control synchronizes the clock. Master releases the bus busy signal when it finished. This is the architecture. This is the diagrammatic representation of basic chaining. And coming to the polling method, control sends address of device to grant a bus access. Each uses priority resolutions here. Memory is equal to highest priority here. The highest priority is granted first, then it does not respond, then the lower priority is granted, and so on until someone accepts. That is one request line and 3-bit grant line. The diagram shows the polling methodology. Coming to the independent, the last one, each master has a request and grant line. The master will receive a clock this common from one side and pass it to the controller, which will derive a clock for transfer. Diagram shows the logical representations of independent. Can accurately predict calculations since memory is always high priority. Thank you so much for listening to my lecture, students. Thank you.